The next time you pull up to the pump, take a second to think about where that fuel actually started its journey. Some of it may have traveled from wells drilled thousands of feet beneath the ocean's surface. Getting it to the surface means placing an industrial facility in one of the most hostile environments on Earth. When a Category 5 hurricane hits, winds top 157 miles per hour. Waves grow tall enough to slam directly into the deck machinery, and the entire ocean begins violently pushing the structure sideways. From a distance, an offshore oil platform looks entirely unsuited for this kind of assault. It is a massive, top-heavy steel structure, sitting totally exposed in open water. Survival in these conditions requires a design contradicting everything we know about large buildings. The platform is not actually designed to remain perfectly still. Not all offshore machinery faces the storm in the same way. A dynamically positioned drilling vessel, which is designed to create or service wells, can simply secure its equipment, disconnect, and drive away from the projected path. Permanent production platforms don't have that option. They process the extracted oil and gas and send it toward shore. Moving one means ripping up an enormous underwater network of wellheads, control cables, and pipelines. They have to stay and endure the weather. So long before the winds pick up, operators initiate a massive shutdown sequence. Subsurface safety valves are closed off to isolate the wells. Crews are completely evacuated from the facility by helicopter. Loose gear and massive deck cranes are locked firmly into their storm positions. A working platform contains flowing hydrocarbons, chemical storage, and high-pressure pipes. If that equipment remained fully active while violently pitching and rolling, one broken pipe could trigger a devastating failure across the plant. By the time the first hurricane-force winds arrive, the platform is entirely shut in. It is no longer trying to operate normally. Its sole objective is to fail safely. Looking at the towering decks and living quarters above the water gives you a false impression of how the structure stays upright. The true stabilizing body is actually concealed completely below the surface. Take the Spar platform design. It is built around a massive vertical cylinder that acts like a deep-sea buoy. Up to 90% of the structure sits underwater, often reaching down 700 feet. By placing heavy ballast at the very bottom of that hull, the platform keeps its center of gravity well below its center of buoyancy, letting gravity constantly pull it back toward an upright position. In this schematic of a tension leg platform, upward arrows show a highly buoyant hull constantly trying to rise, but downward arrows represent long steel tendons anchored firmly to the seabed. Competing forces keep the platform under permanent tension, restricting vertical lift while allowing horizontal sway. A semi-submersible design takes yet another approach. It relies on widely spaced columns supported by huge submerged pontoons. Because the bulk of its buoyant volume sits deep underwater, it entirely avoids the most violent wave action crashing across the surface. While they look vastly different, all three designs share the same engineering philosophy. They do not oppose the immense power of the ocean with absolute rigidity. Instead, their hulls are shaped to respond predictably to the forces pushing against them. But a stable hull can still be blown entirely off its location. To prevent that, a floating platform relies on a spread of mooring lines that extend half a mile or more across the ocean floor. In this top-down map, the platform operates inside a defined envelope. As the ocean pushes it off-center, leeward lines relax while windward lines pull taut. As it drifts, tension creates a rapidly increasing restoring force, represented by growing arrows. This flexibility absorbs massive shock loads. If those mooring lines were to fail, a structure weighing thousands of tons would become a free-floating hazard. A drifting platform can drag massive steel anchors straight across subsea equipment and easily rupture neighboring pipelines. Keeping the platform securely within that envelope is especially critical because it remains tethered to the seabed by long pipes called risers. These carry oil and gas up from the fixed wellheads, and they are built with long sweeping curves to absorb the continuous shifting of the hull above. The hull, the mooring lines, and the flexible risers all operate as a single interdependent system. The moorings limit the hull's travel to protect the risers, and the risers bend to ensure the wellhead far below remains secure. But securing the underwater components doesn't protect the machinery above the surface. In a major storm, the platform faces what offshore engineers call green water. These are solid walls of seawater that launch violently over the decks, striking areas normally only exposed to wind and salt spray. A single cubic yard of that water weighs roughly 3/4 of a ton. When it repeatedly slams into steel framing, it deforms walkways and crushes pipes. At the same time, the hurricane-force winds push against every crane, housing module, and derrick, treating the platform's vast surface area like a giant sail. This top-down assault is why we can't judge a rig's survival based strictly on whether it stays afloat. During Hurricane Aizen, several fixed platforms were destroyed by waves overwhelming their decks, while the deep-water floating hulls and moorings actually performed quite well. The true test during these storms is occurring at the micro level. The hurricane places extreme stress on thousands of individual bolts, fasteners, and heavy tie-downs. Their job is to stop ordinary deck machinery from tearing loose and becoming enormous, uncontrolled moving loads. One failed bracket or sheared cable tray won't necessarily sink the rig, but it can easily disable the specific control systems required to inspect and safely restart the plant. After the storm passes, a helicopter crew might fly over and see a platform that looks perfectly intact, but the most dangerous damage is often entirely hidden. Before any oil or gas can flow again, operators must lower remotely operated vehicles into the water to perform a massive structural audit. They inspect the entire submerged web, checking for bent risers, anchors that may have dragged, and looking for any leaking subsea connections. The ones that do endure rely on a strict sequence of defenses. Weather forecasting creates the time to evacuate. Subsurface valves isolate the flow of hydrocarbons. The hull's geometry dictates how the structure rides the waves, and the massive mooring lines restrict how far it can travel. The towering structure above the waves acts as the visible center of a system that reaches thousands of feet to the seabed. It survives by knowing exactly how much it is allowed to move, relying on a hidden machine of buoyancy, tension, and flexible pipelines to catch it the moment the storm pushes too far.